Hello students, welcome to the module 2 and we are going to solve some numericals based on the concepts which you have understood from the topic. So steady fluid energy equation and how to apply first law thermodynamics to various devices. Okay, so we'll begin with the problem, a very simple problem, so that it is easy to understand the numericals. Okay, so a problem is a steam having a specific enthalpy of 2930 kilojoules per kg flow through a turbine nozzle and after expansion leaves the nozzle with an enthalpy of 2260 kilojoules per kg. If the flow is adiabatic, then determine exit velocity, initial velocity, determine the exit velocity, and initial velocity is given, that is 3600 meter per minute. Okay, see here in this problem concept is the device first you have to understand, that is a nozzle. Okay, there is a nozzle, there are different types of nozzle will be there: converging nozzle, diverging nozzle, or converging diverging nozzle. Okay, for this problem the device first you have to identify. Okay, so that is nozzle and inlet velocity 60 meter per second is given. Okay, so we have to find out what will be the exit velocity, that is what will be the exit velocity, that we have to find out. Okay, so after the expansion it leaves the nozzle with an enthalpy of 2260 kilojoules per kg. Initially it is 2930 kilojoules per kg, and once it is expansion taking place, that is 2260 kilojoules per kg. So this, if the flow is adiabatic, is very important. Why the word they used is adiabatic. You have to understood. We already discussed in the previous theoretical concept of adiabatic wall and diathermic wall, where there is a adiabatic condition of that nozzle, means there is simply you can write it as Q is 0, where they mentioned adiabatic. Okay, and okay, these are the things we have to understand before solving the problem. Okay, let us write down the given data. Okay, so H1 is given 2830 kilojoules per kg Kelvin, and H2 is 2260 kilojoules per kg, and inlet velocity is given in terms of meter per minute. Okay, that we have to consider in meter per second, because all are in SI unit. We have to make it in SI unit, and if you want to convert it to meter per second, you have to divide. Okay, so you will get the meter per second unit. Okay, that is 60 meter per second is the inlet velocity. Okay, and assume that if the nozzle is there, there is no datum line, and Z1 is equals to Z2. Okay, the height is inlet and outlet are same, so Z1 is equal to Z2, and as it is adiabatic, Q is 0 and nozzle performing any work, so it is 0. So now you apply this all the condition to the steady flow energy equation for the nozzle. Okay, what about equation, that is steady flow energy equation? Already we know, that is E1 is equal to E2. Okay, so what is E1? H1 plus V1 square by 2 plus Z1G plus Q is equals to H2 plus V2 square by 2 plus Z2G plus W. Okay, now you apply this steady flow energy equation for the nozzle. So Z1 is equal to Z2, so that term is get cancelled, 0, and Q is also 0 and W is also 0. What else remaining? That is H2 minus H1 plus V2 square minus V1 square by 2. Okay, these are only these terms will be remaining. So you substitute the values. So enthalpy is given already, H2 minus H1, H1 and H2 are given. You substitute and get the value, and only thing is that V2 we have to calculate. So V2 square by 2, V2 square minus 60 square, that is 60 is V1. Okay, by 2 is equal to 670 into 10 power of 3. Okay, after solving you will get the V2 value is 1159.13 meter per second. So this is the final velocity. So always if you consider for the nozzle velocity, obviously it will be increased as compared to inlet velocity. So that is the function of nozzle, to increase the velocity. Okay. So I hope you understood this problem. So similar kind of problem we will solve in the coming slides. But the thing is that, so whatever the number of problems you solve for the steady flow energy equation, first your basic thing is that, so you understand which device is given and what are the things to be applied for the steady flow energy equation for the particular devices. Like this, okay, whether Q is 0 or some value, or W is whether the device is performing work or not. All these things we have to consider, and whether the datum line is given, means that is the height is given. If the height is not given, so you, even if you also assume that Z1 is equal to Z2. Okay, that is, all these things are very, very important. In thermodynamics, some of the cases you have to be assumed. Okay, even it is not given in the problem, you have to assume suitable data, you have to assume and do the calculations. So this is how we are going to solve this problem. Let us discuss some other problem in the next slide. Thank you.